Today we will be learning about matched pairs t-tests. So first of all, before we get started, paired data is when you have two sets of data that are related to one another. So some examples that might be considered pair: if we have some drug administration and we're concerned with blood pressure changing after they administer the drug, so we would take a before reading of blood pressure and an after reading of blood pressure, and we're testing to see if there's a difference. Before and after scores of an SAT prep course. So if we believe that an SAT prep course will influence the score that you get on the SAT. And then another example might be the active ingredient in a name brand versus a generic brand drug. So the reason why we pair is because each individual is their own best control. So if I was doing a study on blood pressure after a drug administration, I wouldn't want to just average everybody's blood pressure before the drug administration and then average everybody's blood pressure after, because a lot of people have differing blood pressures to start with. So each person is serving as their own control. In other words, if I have high blood pressure to start, and then I do the drug and then see the after reading, I can see if the drug really had an effect on my individual blood pressure. Whereas if we average the whole group, we're hiding those differences. Okay, so the hypotheses for this type of test is we are going to be finding the difference between the before reading and the after reading, or the difference between the paired data. So we're going to be using the notation mu sub d. That d stands for the difference. So once I find the difference between each paired data, I'm going to average those differences together. And if it's 0, that's indicating that there really is no difference between the before and after reading. So that would be the null hypothesis. And then the alternative hypothesis is there is a difference between the before and after readings. So do we think it's just not equal to 0? Do we think that the difference is decreasing, causing it to go down? Do we think the difference is increasing? In other words, causing it to go up. So we would use mu sub d not equal to 0, mu sub d less than 0 if we think it's decreasing, and mu sub d greater than 0 if we think that it's increasing. We're going to be using the t-chart for this type of test, and the degree of freedom is going to be equal to the number of pairs that we have minus 1. Okay, so we're going to go ahead and jump into our first example. An SAT prep course claims that they can increase student test scores. Here's the data from 10 students who have completed the course showing their SAT scores before the class versus after the class. At alpha equal to 0.05, is there enough evidence to say that the course increased scores? Okay, so we see that each student's score obviously is different than, not every single value is different, but their pre-scores are different for each individual. So if a person scores lower on their pretest or higher on their pretest, we want to show those differences in scores. So again, each person is their own best control. So we want to see, okay, did the scores actually change from their pretest score to their post-test score? All right, so going through the 6 steps. Step number 1, our null hypothesis is going to be that the difference is equal to 0. That would indicate no change in their score from pretest to post-test. In other words, this class had no influence in their SAT score. The alternative hypothesis, again, we check for an indicator. we're looking for an increase in score. So mu sub d is going to be greater than 0. When I subtract these values, I'm going to be subtracting the post-test minus the pre-test. And that would give me, if it increased, that would give me a positive number. Now, if you decide to subtract pre-score minus post-score, then you would say mu sub d is less than 0, because if the pre-score is lower than the post-score, when I subtract pre minus post, I would get a negative value. So it's not incorrect to say mu sub d would be less than 0, but we do have to indicate the direction in which we're subtracting. Okay, step number 2, I need to find the critical value. So if we're testing a greater than scenario, which I have written on here, I would shade the right tail. We're using an alpha value of 0.05. Oops. This is a one-tailed test. And then I do have to think about degrees of freedom. Sorry, that's really messy, guys. If I do the number of points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I have 10 pairs of data. So I would do 10 minus 1 and get 9 degrees of freedom. Okay, so looking that critical value up on the T-chart, again, 9 degrees of freedom, an alpha value of 0.05 in the one-tailed section. I think that lines up with 1.833 as the critical value. So 1.833 is the critical. Okay, step number 3 for our test statistic, I'm going to fit the formula down here at the bottom. T would equal X bar D minus mu sub D over the standard deviation of the differences, so S sub D, over the square root of N. Again, sorry that's so sloppy. So guys, what we're going to do is we're going to find the difference between each person's post and pre-score. Find that mean. Now, assuming that the null hypothesis is true, mu sub d would be equal to 0. Again, indicating that there's no difference. The standard deviation of those differences we're going to calculate, and again, n is the sample size, which is the number of pairs, in this case 10. All right, so I'm going to go over to the calculator, and I'm going to go ahead and enter these values. I'm going to put in the post scores into list 1 and the pre-scores into list 2, so then I can subtract the two lists. I'm going to go ahead and enter that data, and then I'll come back on to show how we're subtracting. Okay, I have went ahead and entered the post scores in list 1 and the pre-scores in list 2. Now I'm going to go over to list 3, highlight L3, and I'm going to ask the calculator to subtract list 1 minus list 2. So second 1 minus second 2. Again, you need to make sure that L3 is highlighted when you type that in. Okay, the calculator went ahead and subtracted those values for me, so the differences are now in list 3. You do not have to enter list 1 and list 2 into your calculator if you just want to enter the differences into a list 1. That's totally fine too, but we do need the differences between the scores. We're going to go to Stat, over to Tests, and we're going to highlight just the t-test. This is technically now a one sample because I am just concerned with the differences in scores, not the individual scores. So we select option number 2. I'm going to highlight data because I have the numbers in the list. The mu sub d, the null hypothesis, is 0. However, my differences are in list 3, so I'm going to change this to second 3. If you entered the differences just straight into list 1, then you would not need to change that. Our alternative hypothesis is that it's greater than 0, and we're going to calculate. So if I were to substitute values into this formula for step number 3, my average difference was 29 minus the null hypothesis says that mu sub d is equal to 0. So 29 minus 0 over the standard deviation, which is 44.58, divided by the square root of the sample size, which is 10. That is going to give me that t-test statistic of 2.06. Okay. Again, guys, you do not need to write out the formula for me on the homework assignment. You can just put the value from the calculator. Okay, with a t-test statistic of 2.06, and the p-value comes out to 0.069. So that's step number 4. The p-value is 0.069. Notice that p is greater than our alpha level of 0.05. So if p is not low, we do not reject the HO. So we are not rejecting the null hypothesis. So to answer their question, is there enough evidence to say that the course increased scores? We would say at alpha equal to 0.05, there is not sufficient evidence to say that the course increased scores. So we are sticking with the idea that the mean difference is equal to 0. In other words, the course made no impact on their scores. Okay, here is another example of a matched pair scenario. Read through this, see if you can complete those 6 steps for hypothesizing for the matched pairs t-test, and then unpause the video to get the solutions. Okay, guys, here are the solutions to this matched pairs t-test. For step number 1, the null hypothesis, again, mu sub d is equal to 0, meaning there's no difference in pulse rates before and after the drug. The alternative hypothesis, we just wanted to see if there was a difference, so mu sub d is not equal to 0. It's a two-tailed test, the degree of freedom. There were 9 matched pairs, so 8 degrees of freedom. Two-tailed section with an alpha of 0.05 gives us a critical value of positive or negative 2.306 from the t-chart. I went ahead and plugged in the values into stat and edit. I just went ahead and put the before values in list 1, then the after values in list 2, and again I subtracted list 1 minus list 2 in list 3. Stat over to tests, and we select the t-test. I highlighted data. Again, the null hypothesis is 0. We're looking at the differences, which are in list 3, and I highlighted the not equal to case for the alternative. We get a test statistic of negative 1.59 with a p-value of 0.16. P is greater than alpha, so P is not low. We do not reject the HO. So we're not rejecting the null hypothesis. So to answer their question, is there a significant difference in the pulse rates of users at alpha equal to 0.05? There is not sufficient evidence to show a significant difference in pulse rates. So we're saying again that there really is not a change in pulse rates when people use this drug. All right, guys, that concludes notes for today.